Okay, so before we start this current and magnetism, let's just do a brief revision of how a magnetic needle behaves in the vicinity of a magnet. So suppose I have this bar magnet here. This is my north pole, this is my south pole, and I got these 4 points: point number A, point B, point C, and point D. I want you to find out, basically I want you to draw magnetic compass needle at these 4 points. I need to draw them in proper orientation. I want you to stop the video, pause the video for a moment here, and try to draw them. Okay, so this is how they're gonna look, because, and I'll explain as well. So because magnetic field lines are always from north to south pole, here as well as here, and here as well, like this, we need to keep in mind that a magnetic field line can terminate only on the south pole, so it cannot terminate on a north pole. So if I had to plot a magnetic needle here, so this line should terminate on a south pole. Okay, so that means my magnetic needle, compass needle, has to be north, and that has to be south. And likewise, because a line starts from north pole, so you will have another line coming like so. Basically that orientation fits really well in the magnetic field lines. Same is the case here as well. You will have a magnetic compass here like the S and N, and here also not been drawn properly, so let me clean this thing up, and here it will look like this, and there it will be like this. So there are you can draw these compass needles having through two approaches. One approach is that you look at the field lines and then keep in mind that the field lines should always terminate at S pole and should start from the N pole, or they should form a continuous loop, complete closed loop. And the other one is that a north pole will get attracted toward the south pole, and the south will get attracted toward the north pole. So when we use that approach, then also we can see that this is the south pole, it is closer to the north pole here, this north pole closer to the south pole here. Likewise in other cases as well. So here this north is closer to south, this south is closer to north. All right, with that done, let's move on to seeing how different current configurations produce magnetic field. We discussed in the previous video that a magnetic field is produced by moving charges, which basically is electric current. So the simplest current configuration that we can think of is a straight line conductor. So I have a straight line conductor here, and the current is going like this. So to find the direction of magnetic field, we need to use what we call right hand curl rule. So what you do is you hold the conductor with your right hand, in such a way that the thumb stretches in the direction of current. And when you do this, the magnetic field will be indicated by the curling fingers. So if I look at this case here, I got the current going in this direction. So I hold it, and my fingers will go around this conductor. This is my conductor. This is my conductor. My fingers will go around this conductor like this, and that basically indicates the direction of magnetic field. I can show you another picture which is a bit more convincing. So here you can see that the conductor has been, this is the direction of current, and the conductor has been held in the right hand with the thumb stretching in the direction of current here, and this here, the curl of the fingers are going round like this, and that's how your magnetic field is shown here. So that is the direction of magnetic field. Obviously you can see that magnetic field line forms a continuous loop here, and that is, as we discussed earlier, is a necessary requirement for magnetic field lines. We can see this diagram in a different manner. So if we look at this conductor from the top, if we look at the conductor from here, then we'll see current coming towards us. So we can show current like this with a dot. So that indicates the current. When it is like this, then the magnetic field lines, again you can hold the conductor in your right hand with the thumb stretching in the direction of the current. So basically when you hold it, the thumb will be towards you, coming towards you, and your fingers are going in the counterclockwise direction. So that's the magnetic field. Other way is that you see the conductor from the bottom here at this point. So if we watch from here, then the current is going away from us. So it will be indicated by a cross. Cross means current is directly perpendicular into the page. And when it is directly into the page, then the magnetic field lines will be going clockwise, in the clockwise direction. That's the magnetic field. Okay, let's also see how we can determine the value of the magnetic field. We are not going to derive the formula, but we are just going to look at the formula for magnetic field intensity near a straight conducting current carrying conductor. So this is your conductor, and at a distance of r from here, the magnetic field intensity is B is equals to mu 0 I upon 2 pi r. Now we just need to remember that mu 0 here is known as the permeability of the field medium. Mu 0 is a constant. Mu 0 is equals to permeability of free space. Yeah, so it is linearly inversely proportional to the distance. So farther you move away from this conductor, the weaker the magnetic field will go. But just keep in mind that this magnetic field is for infinite conductor, which means that this formula is true only when you're trying to measure the magnetic field intensity closer to the wall, closer to the wire, closer to the conductor. Okay, another current configuration that we are going to see is a current loop. So look at this. This is my current loop here, and the current is going like this. This is I, and that's I. Okay, and this current loop is lying on the screen, on the page. So the plane of the current loop is in the plane of the paper here. Yeah, so they're in the same plane. Now here, if we want to find out magnetic field in direction of magnetic field intensity, direction of magnetic field, we have to use the right hand curl rule again. Same thing. So we we hold the conductor. We can hold the conductor at any point we want. We can hold the conductor in our right hand here. We can hold the conductor in a right hand here. We can hold it here. We can hold it here, and we hold it again in such a manner that the thumb stretches in the direction of the current. Then we see that magnetic field here inside this current loop is into the page, and if it is into the page, then we need to show it with crosses. That's my B here. And when I look outside here, outside I see that because it's going in here, it comes back here. Again, you use your right hand curl rule, and you see that fingers are coming out of here. So the magnetic field is out of phase here in the A region outside the current loop. Okay, so what if we look at this loop from the other side? From this side, we are seeing that the current is going clockwise, and if we plot it from the other side, if we look at it from the other side, we will see that the current is going counterclockwise this time, and the current is going counterclockwise. Then you again use the right hand curl rule, and we find we can, just like the previous case, we can hold the conductor here, we can hold the conductor here, doesn't matter, and wherever we hold, we will find that the magnetic field is out of the phase here in this region within the loop, and outside it will be crossing. And when we look at both of them, we can clearly see that in this picture one, in this diagram, in this case, the magnetic field lines are going into the page. So if you stand on the other side, you will see the field lines coming towards you, and that's what we have in this diagram. Okay, so let me ask you one more thing. So if we are considering this case here, and we see the magnetic field lines going into the page here inside the loop. So what kind of magnetic pole we are looking at when we are looking from this side? So when we are looking from this side, we are seeing that lines are going away from us. Effectively, we could say that lines are terminating there. So when the current is clockwise, from here we will see, when the current is going, that is a cross as well. When the current is going in the clockwise direction, we see that the magnetic fields are going away from us. We see that the magnetic field lines are terminating there. So effectively, what we are seeing is a south pole here. But the same current loop, if we look from the other side, we see that lines are coming towards us. In this, I'm talking about this diagram here. It's the same current loop, and I'm looking at this current loop from the other side this time. And when I look at it from the other side, I see that magnetic field lines are coming towards me. So when the field lines are coming towards me, what I am basically looking at is N pole. So you can see it's the same current loop. When viewed from one side, it looks like a north pole, and when looked from the other side, it behaves as a south pole. So it clearly tells us that you cannot have a single isolated magnetic pole, because just like a coin, the coin, both of them have to be together. A coin has two faces, and accordingly, and in exactly similar manner, a magnet will have two poles. One side will be north pole, other will be south pole. They always come together. You cannot get rid of one pole. Okay, one more diagram I would draw for the current loop. Let's say current loop is like this type. It's perpendicular to the plane of the paper this time. Okay, so when I see this, I can see that we are not sure about the orientation of this current loop. So what I would do is I'll draw the axis of the current loop with a dotted line. Okay, now we can see that this current loop is this side, this side here is is towards us, and that side is away from us. Okay, so if we look at this current loop and the direction of the current is like this, then what would we see here? And within the current loop here, in this region, in this area, the magnetic field lines are coming out like this. And therefore when we see from this side, we will see a north pole, and when we see from this side, we will see a south pole. Effectively, this current loop is nothing but a tiny magnet, where this side is north pole and the south pole. They are equivalent in a way if you want to compare them. Okay, next thing that we are going to talk about is solenoid. Now solenoids are these kind of diagrams. I will just let me show you. What we have here is you have this kind of thing. It's a conductor, current carrying conductor, but it's wound around some core. Yeah, so basically this is a solenoid. The only thing is that you have in here you have a core as well, on which it is drawn, on which this wire is wound. So if we look at this diagram again, that it could be a solenoid. Suppose the current is going here in this direction and coming back out here. I want you to stop the video for a moment here and draw the direction of magnetic field here inside of this solenoid. Yeah, again you use the right hand curl rule, and the current here is like this, and use the right hand curl rule, and you will see that your magnetic field lines are like this. Yep. So these magnetic field lines within this, inside of this solenoid, are quite uniform. So you have a uniform magnetic field within here, and then obviously you have all, because they need to be form closed loops, so you will have magnetic field like this, and these kind of things are known as solenoid. They are drawn in a different manner as well. I mean, if you, for example, if I draw a solenoid like this, now you wouldn't have an idea of the orientation of this solenoid, so it can be confusing. So there are a few other ways it is a solenoid is shown. One way we show is like this, that first we have a core on which the conductor is wound, and then we show it like this. Now that is a solenoid 2, and there you go. This is wire, and that's the wire. That's the wire there. So if the current is going like this, so that's the direction of current, that's the direction of current, that's the direction of current, and magnetic field, again with the right hand curl rule, the direction of magnetic field will be like this. Yeah. Another way it is shown is we just use the dots and crosses. So just the same thing I can show with dots and crosses. So this wire here going here, so at this point the current is coming towards me, so I show that with a dot, and then here it goes into the page again because it's drawn here, so I need to show a cross. So that's dot, that's cross, that's dot, that's cross, and likewise, and we say that there's a current there. again, this is the same content. They are exactly same, this figure and that figure. So magnetic field will be like this. Now solenoids are very important because they can work as some sort of a switch, and they're really important in industry because I can just give you one example. Suppose you want to control, you want to switch on a current of 300 amperes, which is very huge current. So suppose you have a machine here, this is your machine, and that machine takes a current of 300 ampere. 300 ampere is huge, and you have a switch here and you want to control it. You want to turn this switch on so that the current starts flowing into this machine. Can you do that? We cannot do that. We cannot directly turn on and off a current of 300 ampere because 300 ampere is huge. It's very, very large, and when you will turn on and off, there will be a huge spark at this point on the switch here, and it's a huge current, so it may burn the switch as well. You need very high capacity switch here, and it's not practical as well to directly control it. So what you basically need is you need some way of isolating your current control circuit and your main circuit. So this is the main circuit, and what we have here is, what we do is that this is your main circuit and this is your switch. We call it relay switch. Yeah, this is the main circuit, and you have another circuit which just have a small current. Yeah, so you control this main circuit here, you control this circuit by controlling this circuit here, and they are isolated, so they are not connected, so anything happens in this circuit will not affect this circuit. What you do is you turn the switch on here, and this circuit comes into, if the circuit is completed, and you have 300 ampere current flowing in this. For these kind of switches, we normally use solenoid. Yeah, you start the current in the solenoid here, like I'm just showing here. You start the current, this switch will control that current, and when you turn this switch on, the current will start flowing in this. That core will become magnetized, it will become a magnet, and if you have some iron here, some pin or some lever, that lever would get pulled to the magnet, and that would complete the circuit, complete this main circuit here. And you could make that thick so that it could carry 300 ampere current as well. And one last thing, I mean, if we look at solenoids here, what we get is there is a one-to-one correspondence between this solenoid and this solenoid here. This side behaves as north pole because you see line coming from there. This side behaves as south pole here. So that's the north pole, that's the south pole. It's equivalent of a north and south pole. It's equivalent of a permanent magnet, bar magnet. One more thing, whenever you have a loop, just one more thing to cover before we close this window. Whenever you have a current loop, we are here, go back there, and there you go. So we got this current loop here, and this current loop and solenoid, they all form part of electromagnets. So in electromagnet, you would normally have a loop or a solenoid or this kind of thing. So if you want to increase the strength of magnetic field created by this current loop, what can you do? How can you increase it? So one way would be to increase the current, and other way would be to increase the number of turns in the loop. Yeah, so if you increase the number of turns in the loop by 10, so instead of having just one loop, you have 2, you have 3, 4, 5, you got 10, you got that winding, the current looping there going 10 times, you got 10 loops here, then the magnetic field strength here will be 10 times. It is as simple as that. Okay, that's where we're going to stop.